Hello, welcome to our presentation of EC3400, project number 3, about design of an operational amplifier. I am Stephen Kanceruk,
I'm Oliver Moreno.
I'm Zhang.
and let's get started. So, right here is the basic template of what we made our circuit with. As you can see, it has the cascaded output with the purpose of increasing the output resistance, resulting in a higher output voltage and thus a higher gain.
And on the left, you can see that that is similar to the differential amplifier that we've seen in class.
I want to highlight the basic design procedure. So the first thing we did was we used the mathematical relationships to determine the parameters that we were going to be tuning, such as capacitance and resistance, to meet bias current requirements as well as frequency requirements. And after that, we just considered the major trade-offs, mainly that the higher bias current did result in a better bandwidth, slew rate, and noise power performance, but it also resulted in higher power dissipation. We also try to keep the design simple to protect against transistor discrepancies as well as poor noise sensitivity.
On the left, we list the specifications we were given, with checks indicating the ones that we successfully met in this project. We met all the common ones except for the CMRR, and we met amplifier bandwidth and the slew rate for the project specific ones. Also worth noting is the chart you see on the right side with the parameters we used for our transistors in the EKV model.
Here we can see the basic circuits that we use to bias our cascoded PFETs and NFETs, as well as the base transistor. We control the ratio of W over L in the bootstrap circuit as well as the current, and this manipulated as well as the resistance to manipulate the current that we needed. Here we can see a plot of the amplifier gain. This was measured with a DC sweep. The high gain region we see in the middle is where the inputs were close to each other, and we also saw some interesting behavior in some of the other nodes, possibly due to capacitance. And in this slide, we zoomed in so that we could actually measure the slope, and we determined that the gain was 88 decibels.
Here we have a open loop configuration, and we use this configuration to do an AC analysis in order to determine our phase margin. And here in this slide, we see the results of that AC analysis. On the top, we have our magnitude over frequency, and when we find the unity frequency, we take that frequency and we find the corresponding phase, and in order to find the phase margin, we take 180 degrees and subtract it from that unity gain frequency phase. And the result of that is 46.4 degrees, which is within acceptable phase margin. And also, here are two separate configurations which we use to find the common mode gain and the differential gain, and we use that to find the CMRR, or the common mode rejection ratio. And on the chart on the left is a display of our results, and unfortunately we did not meet the specifications of 10,000 or greater CMRR.
Here we measured the slew rate. The procedure for measuring slew rate was just basically a step response. We passed in an ideal unit step, and we measured the rise time in the output. We obtained a satisfactory slew rate of 2.093 volts per microsecond. And as for the power dissipation, we simply place a DC operating point at the power source, and this calculated our power consumption parameter, and this did not meet the desired specification of 250 nanowatts. As for noise performance, we use the expression highlighted in one of the documents as that discusses noise power in operational transconductance amplifiers. This requirement was not met either, and we determined that it was possibly due to the large amount of branches and small control over the resistance. I'd like to add a few final thoughts and to conclude the experiment. We'd like for in future work to reduce the power consumption of in order to use this design in microsystem applications, and in order to do that we need to budget current more wisely and tune the parameters of the transistors to meet this. We would also need to possibly alter the design by adding a capacitor between the P cascode at the output, and we did notice that this improved bandwidth and slew rate, but we could not get it to work with our gain, so that is a possibility. And we could also add a folded cascode at the output branch to improve the and also to improve the input-output voltage rail. We could invert the design by making it a PFET based.
This concludes our presentation. Thank you for watching.